Hi guys, in this video we'll look at the chemistry of alkynes. And this first page shows an overview of the reactions we'll be looking at. Now we will see that the reactions are very similar to reactions of alkenes. The major difference is the alkyne has 2 pi bonds instead of just 1. But because it has 2 pi bonds, typically the reaction can just take place twice. For example, we can react an alkyne with HX, and it will be an addition of HX. And when we do that, we see that the product is actually an alkene. X here and nu H here. And we should be able to understand that regiochemistry by considering the same points we consider with alkene reactions. But the product here is an alkene, and of course that can react with HX again, and we'll see that that gives a dihalide here, but it's a geminal dihalide, not a vicinal dihalide. Of course, our mechanism will show why. Okay, we can also react an alkyne with elemental halogen, but again we can do that once, but then the alkene will react again with halogen, and that will actually give a tetrahalide. Now we'll also hydrate alkynes, and we'll use similar reagents we've used before with alkenes: oxymercuration or hydroboration. The initial hydration of the alkyne gives an intermediate called an enol. And the enol is a shortened term for alkene alcohol. The alkene has an OH group on one of the alkene carbons. Enol. Now, enols are not hydrated a second time. Instead, they undergo a rearrangement by a process called tautomerization, and in this case, the carbon ends up double bonding to the oxygen instead of to the other carbon. We also relocate a single H. This gives a carbonyl compound that can either be a ketone or aldehyde depending on the substitution pattern of the carbonyl carbon, of course. So the enol and tautomerization will be new chemistry here. We'll also see reduction of alkynes. As with alkenes, alkynes can react with hydrogen and a precious metal catalyst to give addition of hydrogen. We call that hydrogenation, or we can call that reduction. I'll leave this discussion to later. One comment I'll make now is that we will see our first radical reaction. Reduction of alkynes to transalkenes, that's a radical reaction involving use of sodium metal and ammonia as a solvent. Okay, that's a very sort of brief overview there. We'll be coming back to that, and you can use this page as reference. This page here, I show you some examples of drugs that contain alkynes or alkenes. Let's get started, and we'll begin with nomenclature, and I'll do that in this video rather than a separate nomenclature video. Nomenclature of alkynes will be just as with alkenes, except we want to use the "-ine" ending. And thus we begin by finding the longest continuous carbon chain. Okay, just as with alkenes. Thus, the alkyne needs to be in the longest continuous chain. So we use all the same rules. Of course, here, the longest continuous chain is just 1, 2, 3, 4, 5. Okay? And so that would be a pentyne. 5-carbon chain with an alkyne in there. Now we need to note where the pi bond is located. This would be 1, 2, 3, 4, and 5. We give the pi bond position the lowest possible number. And so this compound is 1 pentyne. Now note that I drew in the H of the alkyne. That's sometimes common, but you don't have to do that. We could have just drawn this like here. And then we could have just made this last carbon-carbon a triple bond. One, two, three, four, 5. And that is sufficient there. You do not have to draw the H. Got to be careful though, because this is all linear through here. Okay, this is an sp linear carbon. I see a lot of times students lose track of how many carbons are actually here. 1, 2, 3. All right. Now this is actually a terminal alkyne. Terminal alkyne, the alkyne is at the end of the chain. All right. But very importantly, a terminal alkyne has an H. Okay. It's going to have an H on the alkyne, one of the alkyne carbons. Of course, it would be the one on the end. Where an internal alkyne, such as the second molecule, there is no H on an alkyne carbon. Sometimes that may be called non-terminal. One pentyne. Before we name the next one, what if we had a chlorine here or some group here, and what if we put it like this? Well, that's the 4 position. That would be for chloro 1 pentyne. But I also gave specific stereochemistry, and this would be chlorine would be 1, carbon with another carbon would be 2, this carbon would be 3, 4th group is the H, it's back, this is R, and so we would want to put R for chloro 1 pentyne. Okay. By the way, this is 1 pentyne. And what would this be? This is where I see students often getting structure wrong, because this bond here, which is coming off linear, sometimes is not drawn, and sometimes I'll see something like this, and you can't tell if this is another carbon coming off of the alkyne here. Okay, that needs to be clear. Now because of that, you can clarify this is a methyl coming off, and that helps clarify it. But this is what? 1, 2, 3, 1, 1, 2. This would be 2-pentyne. What would this be? What if we had 1, 2, 3, 4, 5? Would that be 3-pentyne? No, that's 2-pentyne. This is 2-pentyne. There's no such thing as 3-pentyne. Okay, be careful how you draw your alkynes. Let's name the next compound. 1, 2, 3, 1, 2, 3, it'd be this way. 3, 4, 5, 6, 7. There's only one long chain, alkyne. 3-heptyne. Note that an alkyne is not stereogenic. The two groups coming off of the alkyne are all linear. You cannot have cis or trans about a alkyne. So there's no stereochemistry here or here. Originally, we did introduce stereochemistry by making this a chiral carbon, and we clarify that stereochemistry with R or S. Okay, let's look at reactions. Again, just as with alkenes, except a few additional considerations. We have a pi bond. We have H plus, Cl minus. Pi bond can react with H plus. Where do we want to leave cation, on right or left? Well, the answer would be left, and so we swing away from the left, and we get boom, boom, boom. Here's where we have to be careful. 1, 2, 3, 4. 1, 2, 3, 4. All right. I kind of want to draw this zigzag. New H here. Why did I put it up? Well, I just drew the zigzag down. I could have did it either way. Either way. There's no stereochemistry here yet. And we'll say why. So there's a new H on the end. We're drawing in all the H's. Okay. Actually, no. There is no H here. No H there, yeah? How's there an H there? There's no H there. These electrons are coming over here, and we're getting this bond, and leaving that as a carbocation. Now that carbocation is actually still linear. It's actually 1, 2, 3, 4, 5. It's actually linear because it's got two regions. SP, linear. So the original carbon was linear. It's still linear. I drew it zigzag because I know where we're going. We're going to an alkene, and the product is now going to be sp2 trigonal planar. But that just, we get our product by these electrons then adding to the carbocation, and that gives that product. And so that is just a simple addition reaction, just like we've done with alkenes. But because we started with a triple bond, we have or 2 pi bonds, we have 1 pi bond left. Now, just a side note, some books will talk about the very high instability of an sp cation. Okay? They will talk about this is bad. That's actually worse than a primary carbocation. And you'd have to think about why. It's just the opposite of an anion. If this was an anion, it would be more stable as more S character. But with cations, it's just the opposite. But I'm going to show the mechanism this way, and some books do, but some books get into a deeper discussion about such cations. Okay, but we can see a simple mechanism to give us this. But this alkene can then react again, and let's do that again. We have H+, a second equivalent of HCl. Where are we going to make cation at, left or right? Well, the answer is again left. And so we get boom, 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 boom. All right, we added the new H on the end, chlorine there, but now there's a carbocation there on that second carbon. We just made that bond, and we made a secondary carbocation bonded to two carbons as opposed to a primary carbocation. But there's a more important reason of why we made this cation, and that is resonance. The existing atom here has a lone pair. And that lone pair can stabilize this cation, and these electrons, we can have them move in here. And this is actually a resonance structure. Double bond, Cl, two lone pairs. Now the chlorine is positive. I'm not going to draw the new H there any longer. This is resonance, and we showed, or we used a resonance arrow. Now, this is something we would have done during week 1 if we were drawing good Lewis structures. If it looks like this carbon needs another bond, well, we're going to ask the lone pair next door to come in here and share and make another bond. But the chlorine, how likely is the chlorine going to be willing to share its electrons? Chlorine is pretty electronegative, and so it may not want to share much. And so instead of a full sharing, this could just be sort of a partial sharing. And instead of the chlorine taking on the full positive, maybe it's just only a partial positive. And instead of this carbon going fully neutral, it can maybe just go towards partially towards neutral and still be partial positive. And this is sort of like what's really going on here, and this is called the resonance hybrid. And when we start doing resonance, we will always talk about that none of the actual resonance structures are real. The real structure is a composite or a hybrid or a blend of these structures. So this is what this intermediate really looks like. But that's cumbersome to draw because it's partial bonds and partial charges. Instead, we organic chemists draw these sort of discrete structures, and just talk about how the true structure is a blend of these. Now this one's actually major, and this one's minor. You can put this in your notes for now. I think the main thing here is the charge is delocalized to the chlorine, where here the charge is just sitting on carbon. But by invoking resonance and understanding resonance, we actually know that some of that charge is actually sitting on the chlorine. So this is the more major reason of why the carbocation is formed here. Although just looking at it as secondary would get you the right answer. So the next step is, after we form our carbocation in the right position, then the chloride comes in and attacks. And that gives a second chlorine on the same carbon. It's a dihalide, but it's called geminal, like Gemini or twins. These two chlorines are twins on the same carbon. Now a little bit more here. The chlorine, or the chloride, we could have used this resonance structure, and we could have attacked here. See, there's a dipole here. We can consider dipole. There's really some partial positive there. If we attack here, we then move these electrons back up, and that gives the product. Of course, the chloride is attacking neither one of these structures. It's really attacking the true structure. It's attacking here and just pushing these electrons. That chlorine was sort of making a pinky bond, sort of pushing them back up. But again, we typically don't do mechanisms with our hybrids because working with these partial bonds is a little bit cumbersome and prone to be confusing for beginning students. Okay, we've covered these two here. So in summary here, we just did a addition of HCl twice, but we recognized that the formation of the second carbocation was going to be here. Yes, it's secondary, but the more important reason is it's resonance stabilized cation. And we stabilize the cation by resonance. Okay, reaction with chlorine or bromine. Very similar. We got Br2. These electrons attack here. Kick these off. Boom, boom, boom. Okay, I'm going to go ahead and draw this zigzag, even though that's not right. Now, the way I'm drawing it, I'm going to put the bromine up. Okay, it doesn't matter, but to keep you from asking that question, I'm going to do it upwards. Same exact thing. Upwards, and put the bromine here. I'll draw in that H that's there. Cation here. But this is NAF because the new group has a lone pair and it's going to back bond. We get here plus Br minus, which we formed here. At this point, this will come in and attack where? Here, same place we made cation. Kick that off. And that will give this product. And again, I see that's going to look like the bromine is up. If we draw this, it's going to be here. The bromine is up. This bromine is going to be down. And that will have to push the propyl group up. All right. But these two are the same exact compound. This is E. There's no other difference. And so I know sometimes you guys get so concerned with, well, the bromine should be up. Well, or down. When it doesn't matter, it doesn't matter. Importantly, this is E. The bromines are going to be high priority groups and opposite here because it comes in backside. Now that's not a tetrahedral carbon, but we're still kicking off a leaving group from the carbon. It's going to be backside. That's why the groups are E and not Z. Now, alkene can react with a bromine again. We add a bromine to each carbon. You know the mechanism. And this product has no stereochem. There's no stereochemistry at all. There's no chiral carbon. There's no stereogenic alkene. Nothing. Just put a bromine on each alkene carbon. And that's just an alkene reaction. You actually did this reaction in the lab, reaction of an alkene with bromine. But we end up with 4 halogens, and so we can call it a tetrahalide. Let's look at hydration of alkynes. This is often done including mercury. Okay. I'm going to tell you to just ignore it. Because we're going to do the mechanism just ignoring it. It can be done without mercury. But usually in a textbook and on some type of standardized test or exam, you'll usually see the mercury there. Of course, it'll be like mercury acetate or mercury sulfate or something. But let's do the mechanism with just good old aqueous acid. H plus and water. Alkyne attacks H plus. We're going to leave cation on left or right. That would be on the left. Okay. Sort of like it's secondary, it's bonded to 2 carbons, as opposed to over here it would only be bonded to 1. At this point the water attacks, and that's going to give boom, boom, boom. Okay, yes, there's 2 H's there. Let's not draw them in. Water added. Get this intermediate. Now something can take an H. There's got to be a minus here. Maybe we use sulfuric acid, and thus we have bisulfate. Or we can just use water to take the H. These electrons stay behind. What does that give? Well, that gives the enol. Just like with alkenes. except we do have one pi bond remaining, so this is a alkene with an alcohol, enol. Now, enols do not undergo a second hydration. Over here we did a second, we repeated. But not with enols. Instead, they undergo a rearrangement. That is, the formula remains the same, just a rearrangement called tautomerization, and that's explained in the paragraph above. Now the brackets mean that the intermediate is not isolated. In the reaction it's formed, but then it quickly continues on and the rearrangement reaction or process takes place. Now we still have acid here. There's still acid present. That's important. And this is an acid catalyzed rearrangement. And it may look a little bit peculiar or daunting, but it's actually very straightforward. And it's actually almost a just repeat the reaction, but we're not going to exactly repeat. But the first step will be of repeating. The pi bond reacts. Where are we going to leave cation at, left or right? And the answer is left. New H there, cation there. And that is very similar. Okay, that is secondary. But there's something we need to do here. What did we do over here when we had a carbocation and the next door atom with a lone pair? Resonance. We're going to do the same thing here. These electrons are going to be attracted here. We can move them in and we can get, this is a resonance structure. New H there. Double bond between the carbon and oxygen. H there. One lone pair remaining. And the oxygen is now positive. You see our resonance arrow. And I may not have said it earlier, but whenever you do resonance, all you're doing is moving pi electrons. You never move any atoms. And that's what we did here. If you think about the hybridization of this oxygen, it is sp2. One of the lone pairs is in the p orbital. Where are we going? We're trying to get a carbonyl compound. That's the rearrangement that takes place. But look what our resonance has done for us. This looks very much where we're going. All we need to do now is remove the H. Well, there's got to be a minus here, okay, bisulfate, or we can use water again. Take the H, these electrons stay behind, and there we go. So it's not a second hydration, but it is sort of a second reaction that follows some of the basic principles. You can sort of think of it as, instead of an external water attacking the cation, it's sort of like this internal oxygen attacks it. But this doesn't lead to another oxygen added to the molecule. It's the same formula. Ultimately, it's just a rearrangement. It's called a tautomerization, and this is our tautomerization mechanism. Now, a good way to remember the mechanism for tautomerization is Oreo. Now this is a mnemonic device, but you're not going to find it in any textbook because I just made it up a few years ago. It's my own mnemonic. What does Oreo stand for? It's like the cookie, like an Oreo cookie. Well, let's look at the steps of the mechanism. The first step was H plus on. And H plus was put on the molecule. Next, we did some resonance. We showed resonance. Now, that's actually not a step in real life. It's only a step on our paper. So we have O for on, Re for resonance. But what did we do in the last step? We took a proton off. Oreo. Oreo. And that can help you remember the mechanism for any tautomerization. Now, under basic conditions, it's just the opposite. This was acidic conditions. Under basic conditions, it's off, resonance on. Because under basic conditions, you typically take protons off, and that would be the first thing you do. We will see that later, but it's still Oreo. Okay, let's make sure we know what a tautomer is. These are tautomers. Tautomers only difference by relocation of a single hydrogen and relocation of at least one pi bond. That's what we did. The H has been removed from oxygen, and it's now on that carbon. There's the H. Okay, we can draw it in blue. It's now there. And relocation of at least one pi bond. The pi bond used to be between carbon and carbon. It's now between carbon and oxygen. And we accomplished that in this mechanism. The first step was adding the H where we need it. And then after resonance, we took it off of the oxygen. Okay. Need to be able to recognize tautomers. We just explained why these are tautomers and what a tautomer is. Question: which of the following are tautomers of the compound in the box? Label the tautomers as either an OH tautomer or a CH tautomer. It's also discussed above. Please do that on your own. We'll look at that later. Question: are the following two molecules tautomers? And then finally answer the question below. Tautomers can more broadly be called which of these terms? Okay, let's finish up this video by looking at another way to hydrate an alkyne, and that is with our hydroboration oxidation reaction. BH3 is electrophilic. The pi bond can attack the boron. I'm going to leave cation on the left. That would give boom, boom, boom. I'm going to draw the boron up. Again, it doesn't matter. I could have did this upwards. It does not matter here. We will see why. H, H, H. Boron is minus. Cation here. This is NaF because this is going to push these electrons away from the boron, and we can actually take these electrons and move them over here. Hydride shift, 1,3 hydride shift that is common with the hydroboration. Boom, boom, boom. And we're going to get, I'll just condense that, and the new H is here. And this is in step 1. We added BH3 to the molecule. Here's BH2, here's the other H, but importantly, these two are going to be cis. Because we know the hydroboration is a syn addition. Okay? Then we come in here with the magic step. What does it do? I'm going to just redraw this. Okay, with the H2O2 hydroxide. Magic. Boom, boom, boom. Well, we just replaced the boron with an OH. But if you remember, no change in stereochemistry. We noted that before when we talked about the magic step. And here's the same structure I draw here. This is the enol. But the enol is not stable. It will undergo a tautomerization. Okay, we didn't talk about the stability over here. The reason this tautomerization takes place is because the carbonyl form, the keto form it's called, or carbonyl form, is more stable. That's largely because a C double bond O is more stable than a C double bond C. And that's largely because the C double bond O is more polar, and very often more polar bonds tend to be more stable. But a carbonyl is a very strong bonding arrangement, and so this is thermodynamically pushed towards the ketone. Now each step here is reversible. Of course, resonance is really not a step. So this is really an equilibrium, as I showed with my equilibrium arrows, but the carbonyl form is highly favored. Except in special cases, okay? So this is going to rearrange to a more stable carbonyl form, but what will that be? Please draw that. Please answer the question here. Okay. Now that's magic, but this, to give final product, what is the mechanism? That's not magic. Now this is a tautomerization. I told you a way to remember tautomerizations, Oreo. We are under what conditions? Basic conditions. We have hydroxide. So you want to do that not on resonance off, but off resonance on. And so the first thing you want to do is, which proton do you want to take off? Think about that. You need to know what you're trying to form. That will tell you which proton needs to be taken off. We will finish this up in class. In the next video, we will move to finish up the remainder of the handout, looking at reduction of alkynes, including a radical reaction, and we'll also look at the acidity of terminal alkynes, and that will finish up the chemistry of alkynes. The handout does have a few miscellaneous pages. A drug with an alkyne, another drug. You can do R and S, D or L. There's also a drug synthesis that I will refer to. And over here is an example of a alkyne reduction or hydrogenation in a drug synthesis. Okay guys, that finishes up this video here. You see the chemistry is very similar in many regards to alkenes, same mechanistic thinking. I think one of the key things though we introduced is the idea of enols tautomerizing to carbonyl compounds, and the mechanism for that, recognizing tautomers. Okay guys,